Right. If you're in grade 12, then you're in luck because you are finding me about to do some differential calculus, just a bit of differential calculus. We're going to look at the concept of finding the derivative using first principles, right? So for grade 12, if we are looking at calculus, right? And we are specifically looking at first principles. What's noteworthy here, guys, is that we have a formula that we get from the formula sheet, all right? And this formula is used to find the derivative of any polynomial expression, or in fact any expression or function, all right? We can find the derivative using first principles, right? Typically in the exams or any test, the first principles question is usually the first question that is asked in any calculus sort of like question, okay? So it is of importance then to know how to use first principles to get the first, or to get the derivative of a particular function. So we're going to look at a few examples. So the formula is basically we say f prime x as the limit of h approaches 0, f of x plus h minus f of x over h, right? So this is the formula that they use to find first principles. And so if we are given, let's say this is the function that we have, f of x is equal to x squared plus 3x, and what they ask us then is to find the derivative of this function using first principles. So what we need to then note is that we need to use this formula to be able to find the first derivative of this function using first principles. So if you can see, there are components of the formula that we need to have first in order to be able to utilize this formula. Firstly, we need to have f of x, which obviously we have. F of x is equal to x squared plus 3x. Then we also need to have f of x plus h. So in other words, we need to just simply take this function, which is f of x, and all we need to do is, in the place of x, we need to substitute x plus h. So where x is in this particular function, we need to substitute x plus h. So we go ahead and we do that, x plus h, the whole thing squared, into 3 into x plus h. So you can see, guys, that where x was, all right, now because we're finding f of x plus h, it means we are going to substitute in the place of x plus h. So where x is, which is here, we're going to use brackets. We're going to substitute in the place of x plus h, and then you can see the square, that's the square that was there, plus 3, this 3, in the place of x we substitute x plus h in brackets. And what I'm going to do is, before I plug this into this formula for first derivative, I'm just going to actually find out what the expression of f of x plus h is, all right, on the side, okay? So then that means x plus h, the whole thing squared, we're obviously going to open two brackets, which I'm hoping we all understand. We don't square the first term and the second term, but we open two brackets so that we can FOIL. And then of course the 3 into x plus h, we are going to use the distributive law. Take the 3 inside the x, take the 3 into the h. So what we then do is we FOIL. X times x is x squared, x times h is plus xh, h times x is xh, and then h times h is h squared, right? Then furthermore, we take the 3, we distribute it inside the binomial there, 3 times x, which is positive 3x, and then 3 times h, which is positive 3h. Okay, then we check, are there any like terms, right? And obviously the x and xh is a like term with the xh, so then we say x squared plus 2xh plus h squared plus 3x plus 3h. So this here is f of x plus h. So I personally advise that if you have the function of f of x, which is x squared plus 3x, find f of x plus h on the side so that you can actually then know what the full expression of f of x plus h is on the side. Then after doing that, you can now take your f of x, go plug it into the first principles formula, okay, so that you can find the derivative. You can also take your f of x plus h, the expression, and go and plug it in where f of x plus h is. So that's what we are now going to do. Now we return back to our first principles formula, f of x plus h, the limit as h approaches 0, where f of x plus h is. What are we going to substitute? We're going to take this little baby here and go make it part and parcel of that f of x plus h. So that means we're going to have x squared. We need to make sure that we're writing it correctly. F x squared plus 2xh followed by plus h squared followed by plus 3x followed by plus 3h. The absolute precision and accuracy need to happen when you are writing this down. Make sure whatever was there, you write it down as you actually wrote it there, so you don't make any error. Then there's a minus sign that follows, that is before the f of x. So this is where f of x is, so I'm going to use brackets and write x squared plus 3x over the whole thing over what? Over h. Yeah, so I hope that sort of like makes sense. Can we see that? Okay, as per the formula. All right, then there at the top, we are just going to make sure now we sort it out. Take the negative, distribute it inside that bracket. Very important, because that minus sign, that's why we put it in brackets. We put f of x in brackets so that we can ensure that the negative sign is distributed to the two terms. So then we have negative x squared minus 3x. It's all over what? Over 8. Let's not forget the limit as h approaches 0. And of course, we are all working towards finding the derivative of that particular function, which is x squared plus 3x. So let's go. Now, like terms, it's time for like terms. So x squared minus x squared will give us 0. So this and that, goodbye. 2x plus 2xh will remain, it's not going anywhere. Plus h squared will remain, not going anywhere. The 3x has a like term, minus 3x. So 3x minus 3x gives us 0. So 3x and negative 3x, they disappear. We are left with 3h, okay, over what? Over h, okay. And then the limit as h approaches 0. You might say, oh, what do you mean life could have been easier if we could only use first principle? Oh man, your comment is killing me. Okay, then in the numerator, all we now do is we take out the highest common factor. So we say like terms, okay, so we substitute, distribute the negative sign, like terms, take out the highest common factor, which is h. We take out that factor specifically because we want to cancel it in the denominator. So if you take out h for the first term, that means we are left with 2x. If we take out h for the second term, it means we are left with a single h. If we take out h for the last term, we are left with positive 3 over what? Over h. And let's not forget this guy. Right? Of course, this say h and the h will cancel because we can cancel. as long as it's not across an addition or a subtraction sign, we can cancel, because the relationship of the h with this bracket is multiply, and we have a divide line with h, so we can cancel those two. We can clearly cancel as long as it is not across an addition or a subtraction sign. Then the limit h approaches 0. This is the expression that we have. All we now then can do is that the limit as h approaches 0, now we can substitute. We drop the limit as h approaches 0, and then we substitute into the h, the 0. When we do that, this falls away, very important, and we are left with the expression 2x plus 0 plus 3, which in essence is actually 2x plus 3. So the derivative, the first derivative of x squared plus 3x, which is f of x, is actually equal to 2x plus 3. And that is how we utilize first principles, which is in the formula sheet, like I said, to basically be able to get the first derivative of a particular function, right? So hopefully that I hope that's very easy to do. All right, this is a good 5 mark, sometimes 6 mark question. All right, and it usually features at the beginning of the calculus questions in paper 1. All right, so you guys need to make sure that you are able to answer how to use the first principles definition to be able to get the derivative of any particular function. And just quickly to recap, like I said, so this here f prime x is equal to the limit as h approaches 0, f of x plus h minus f of x over h. This is the first principles formula or definition, if you want to call it that. Then basically what we do is we can see that it has components. It has the f of x plus h component. It has the f of x component, which is a separate term from the f of x plus h, separated by a minus sign, over h. All right. So we are given the function, which is f of x. F of x means y, of course, but f of x is functional notation, and x squared plus 3x is the given function. So where f of x is, it means that's where we would place the f of x. F of x plus h we don't have, so what we do is we take the function, we substitute x plus h in the place of x, which means everywhere where x is for the function, that's where x plus h will feature, there and there. Hence in brackets we put x plus h, in brackets there we put x plus h. Then we open 2 brackets to accommodate the fact that it's x plus h, the whole thing squared. We open 2 brackets, we FOIL. In other words, we multiply the first terms, we multiply the outer terms, we multiply the inner terms, we multiply the last term, and we get x squared plus xh plus xh plus h squared. Then we take the 3 positive 3, we distribute it into the 2 terms there. We get 3x plus 3h. Then we add and subtract like terms. So there, when we add and subtract like terms, we know that like terms have the same variable and they have the same exponent. Hence, in this particular expression, we can only see xh and xh having the same variable and exponent. So that's why basically we get 2xh. But for all the other terms, there are no like terms. So we leave the expression just like that. So that then means in the place where f of x plus h is, we can substitute these terms. 1, 2, 3, 4, 5 terms, all of them. We go back to the first principles formula. We substitute f of x plus h where f of x plus h was. There it is, all 5 terms, 1, 2, 3, 4, 5. And we are very meticulous and very accurate in writing down the expression as we see it after having expanded and added like terms there. So we substitute f of x plus h in this place there, followed by minus what? F of x. What is f of x? F of x is x squared plus 3x. So in brackets, we are very careful because the minus sign does damage to everything that's inside this bracket. We make sure that there's the minus sign, we put the bracket, then we distribute the negative sign inside the bracket, which changes x squared to negative x squared, changes the plus 3x to negative 3x. Then we add and subtract like terms. After adding and subtracting like terms, we make sure that we have the expression that will all have the h's. We take out the common factor hy so that we can eliminate the denominator. All right, through simplification, we're left with 2x plus h plus 3. When we are at this stage, we are now ready to basically check when 0 is substituted what the expression will be, and that would be the derivative, because as h approaches 0, that is the derivative of f of x is 2x plus 3. There it is. Okay, step by step. Okay, let's look at another one. Okay, if we were asked to find from first principles, remember we always do first principles, we derive using first principles only when it is explicitly asked in the question. So if it says here, determine f prime x from first principles, then we know, we just go to the formula sheet, we go and utilize that beautiful formula that I've just shown you, showcased to you. Let's just look at another one. It was x squared plus 3x. Say if f of x is equal to 2 over x. All right, yeah, let's look at one where there is a fraction. Okay, they say we need to find from first principles f of x is equal to 2 over x. So how do we navigate this space? Okay, so first and foremost, again, the components of the particular formula or the definition of first principles is that we need to have f of x plus h and we need to have f of x. So f of x we already have, it's 2 over x. F of x plus h though is 2 over x plus h. Okay, very importantly. So at least here there's no expanding and all of that. We just have f of x, we have a f of x plus h. Now we can use the definition. Limit as h approaches 0 of f of x plus h minus f of x over h. Seems like we're ready to rumble, ready to rumble. F of x plus h, what will we substitute there? We're going to substitute 2 over x plus h minus f of x. We substitute 2 over x. The whole thing over what? Over h. Okay, certified hand. You guys are killing me there in the comment section. Okay, Hamidu Aziz, good evening to you too. Alright, sorry guys, I wasn't reading the comment section that much there. Okay, so where f of x plus h, there it's 2 over x plus h. Where f of x is, we have 2 over x over h. Now, this is what I call algebraic gymnastics, you know. So we're gonna do some algebraic gymnastics here, addition and subtraction of fractions. Okay, so the addition and subtraction of fractions. So we have 2 over x plus h minus 2 over x, and what we want to do is we want to subtract the two fractions. Now when we add and subtract fractions, we usually add and subtract using the LCD, because remember, you can't add and subtract fractions until the denominator is exactly the same. So what we do is we find the LCD. But you see, there's a kind of, like, you could say, a shortcut that I usually tell my learners to utilize when it comes to the subtraction of fractions, especially when there's two fractions. All you need to simply do is you need to like multiply that and that. So that's the first step. Then you multiply this and that, that's the second step. And then you multiply this and that, that's the third step. So just follow along with me here. I know most of you probably do know how to subtract fractions using the LCD, which is great, and I'm happy for you. But I simply use this when it comes to two fractions. If there are two fractions, you can just simply use this. But if there are more than two fractions, then of course you use the LCD straight up, okay? Because this method won't work. So let's multiply. X times 2 gives us 2x. H x plus h minus 2, x plus h times negative 2. Very important, because x plus h here is a positive value, whereas this 2 is a negative 2. So that means negative 2 into x plus h over. So the whole thing we write over. Then what's x plus h times x? That's actually equal to x into x plus h. Okay, hopefully that makes sense, guys, and I hope you can see what has just happened. Okay, this would be the same thing as saying what is the LCD of x plus h and x. Of course, the LCD of x plus h and x would be the product of x and x plus h. That's what it would be. Then what you would do is you would try then to form each denominator in harmony with the LCD, which is x into x plus h, which means that what would you multiply x plus h with in order to get this LCD? You'd have to you multiply this with x, and you do the same at the top. So you do see where the 2x comes from. Then same thing here. What would you have to multiply this denominator with to get this LCD? You would multiply by x plus h. But what you do at the bottom, you do at the top, which is why this x plus h is there. So hence I'm saying the shortcut here is to just take this x, multiply with the 2, you get 2x. Take this x plus h, multiply with the negative 2. Remember, negative 2, you write in brackets x plus h, over, you multiply the denominators. X times x plus h gives you x into x plus h. I'm going to explain it one more time. You take this x, whenever you have two fractions, you are adding or subtracting, and the denominators are not the same. You take this denominator, you multiply that numerator. That's your first step. 2 times x is 2x. Simple, right? You take this denominator, x plus h, you multiply this numerator, negative 2, that gives you negative 2 into x plus h. Then last step, you take this denominator, x plus h, you multiply this x, you get x into x plus h. Simple enough? I hope it is. Then you're asking yourself the question, where does this h disappear to? Then all you do is you say divide. You actually literally write out divide. Divide by what? Divide by h over 1. Because in reality, this is divided. The line means divide. Divided by what? By h. So I'm writing it out explicitly, and I'm saying this entire fraction divided by h. But h would be written as h over 1. Are you with me? Then check this out. So then of course now I'd go ahead and actually distribute the 2, negative 2x or negative 2x, and then my negative 2 times h, negative 2h. Okay, and let's just leave this one undistributed. Okay, then the divide. You remember with fractions you would usually say if you have 4 over 3 divided by, let's say, 2 over 3. In fractions, we know that we can change the divide to multiply, and what happens to the second fraction? It inverts. So you write it as 3 over 2. Okay. Right, for those that are coming in, this is grade 12, guys. We're doing calculus, okay? It's grade 12 calculus. So yeah, we're looking at deriving using first principles. So this is calculus grade 12. So 4 over 3 times 3 over 2. So the divide would change to multiply, and then you would invert this fraction. It becomes 3 over 2. I hope you can still remember that. And then of course you can now do this. As long as it's numerator denominator relationship with multiply, 3 and 3, they go into each other. The highest common factor between 3 and 3 is 3. 3 goes into 3 once, 3 goes into 3 once again. Then the 4 and the 2 as well have a highest common factor, which is 2. 2 goes into 2 once, and 2 goes into 4 2 times. Then what you do is you would multiply 2 times 1, is 2, and then 1 times 1 is 1. So hopefully you can still remember this basic manipulation of division between two fractions, that you could always change the divide sign to multiply, and then the second fraction, it inverts. It actually is expressed as a reciprocal. So we're going to use this same principle here. Remember, I said this fraction at the top divided by h. So in other words, I wrote it down divided by h over 1. But then now I'm going to change this divide to multiply, and then I'm going to write 1 over h. Okay, so hopefully you guys can see that 1 over h, the limit h approaches 0. Okay, now I'm sure you guys can see that in the numerator there seems to be some manipulation that can yet be done. So I'm just going to continue this question here. Sorry, let me just remove my beautiful pen here, my beauties. All right, let's remove them. Limit h approaches 0. 2x minus 2x, that's 0. Okay, because we're adding like terms there. That leaves us with negative 2h in the numerator. In the denominator, we have x into x plus h times what? 1 over h. But I'm sure you can see that there's further simplification that can happen here. Okay, yeah, we're left with negative 2h at the numerator, 1 over h. So this here, this h and this h cancel. Okay, does that make sense? Because h divided by h leads me to 1. And then ultimately, what am I left with? I'm left with negative 1. Okay, remember, this is now 1 over 1, which is 1. And anything multiplied by 1 is basically that thing, if that makes sense. So here we are left with negative 2 times 1, which is negative 2 in the numerator over x into x plus h. Okay. And let's not forget the limit as h approaches 0. Okay, we are not done. Now we are ready to do what? We can substitute that 0 in the place of h. Okay, that gives us what? Negative 2 over x into x plus 0, which is actually equal to negative 2 into x times x is x squared. That x times 0, obviously the x plus 0 gives me x, so therefore I say x times x gives me x squared. So this here is the derivative of what? Of 2 over x. It is actually negative 2 over x squared. So I'm just going to go back a little bit to the question itself. This question was asking me to determine f prime x from first principles. And this was the function. F of x is equal to 2 over x. So you guys will remember that I said the formula for first principles is f prime x is equal to limit as h approaches 0 of f of x plus h minus f of x over h. The two components that I need so that I can be able to get first principles is to firstly get f of x, which is obviously there, and then I have to get f of x plus h. How do I get f of x plus h? In the place where x is, I substitute x plus h. So where x is, I substitute x plus h, and that's what I get, 2 over x plus h. So there it is. In the place of f of x plus h, I have 2 over x plus h minus what? F of x, which is 2 over x over what? H. Then what we have to do in the numerator is we need to subtract these two fractions. When we do so, I showed you guys just a concise, clear, to the point method where you can just find the LCD. But the most concise way when you have two fractions is you can take this denominator, which is x, you can cross multiply with the numerator, for your first step. So x times 2 gives you 2x. Then you can take this denominator x plus h, times it with this numerator, which is negative 2, which gives you negative 2 into x plus h. The whole thing over what? X plus h times x. You multiply these two for your third step, which will give you x into x plus h. Now, this here is a divide line, all right, and it's over h. So what I can say is, I can, instead of writing over h, I can just write divided. I can divide this entire fraction numerator divided by h over 1, all right, for convention. Then what do? Take this negative 2, distribute it into the x, I get negative 2x, minus 2 into plus h, I get negative h. The whole thing is over x into x plus h. This division sign changes to multiply. All right, when I do that, the whole purpose of doing this is because if you remember from earlier grades, whenever we'd have two fractions and there was a division sign in between, we could change the division sign to multiply. And then the second fraction, what would we do to it? We would invert it. So this means that this 2 over 3 becomes 3 over 2. And then we can simplify. So we're doing the same thing here. We change the divide to multiply. And then after changing the divide to multiply, what happens? We can now actually simplify further. 2x minus 2x gives us what? 0. And then we are left with negative 2h in the numerator. There it is. Over what? Over x into x plus h. Times what? Times 1 over h. Okay, and then this h and this h, the relationship between minus 2 and h is multiply. We have times and then 1 over h. But since this is in the denominator, that's in the numerator, those two can cancel, because cancellation can happen as long as it's not across a addition or subtraction sign. So this h and this h, they cancel out. We are left with negative 2 in the numerator. We are left with x into x plus h in the denominator. 1 divided by 1 gives us 1, but we know that whatever we multiply with 1 is actually whatever we have. So that's negative 2 over x into x plus h. Remember, the limit of a as h approaches 0 was always there all along. Now we can actually apply it, and in the denominator, when we do that, we get the x plus 0, which is x. X times 2 gives you x squared, and then in the numerator we have negative 2. So that means f prime x is equal to negative 2 over x squared. Okay, that was not that difficult, guys. I hope it wasn't, and I hope there's sort of like a level of fluency as we do this particular problem from first principles. Okay, so I did do sort of like a quadratic function type function so that you guys can see that any quadratic function, when we apply the first derivative to it, we get a linear function in actual fact. All right, now this here is a hyperbola function. The derivative of the hyperbola function is basically derived, and we get a negative 2 over x squared. All right, so yeah, I hope you guys kind of see what it is that is happening as we derive from first principles. Okay, all right, and maybe we can do one last one from first principles. All right, but I hope you guys saw how we were able to do this one specifically, the f of x equal to 2 over x, deriving from first principles. F of x is equal to 2 over x. Okay, and then how we were able to derive this one, f of x is equal to x squared plus 3x, how we were able to derive that one. So these components, I actually sort them out outside, especially f of x plus h, because there's a lot of algebraic manipulation that needs to happen where you have to multiply out, FOIL, add and subtract like terms. So I sort that out outside, and then after I've gotten it, then I substitute it into the actual first principles formula, so that I can then work out this in its simplicity within the formula. Okay, right, So guys, if you have any questions, please do let me know in the comment section. If there's anything that you want clarity with, maybe yeah, whatever it is, guys, I'm here for that, to help us be able to not be confused or lost or whatever the case may be. Because first principles, like I said, for calculus is very important, it's very key. You guys need to know how to answer first principles questions as a grade 12 learner. Yeah, it's very important. Okay, and maybe what you guys can do, let me leave these one. So from first principles, okay, let me leave you some game challenge problems to do on your own time, and then maybe when I go live, let's say tomorrow around about the same time, then I can actually pick us up from where we left off. Derive from first principles and determine f of x if f of x is equal to 3x squared minus 2. So that would be your first one. Your second one, f prime x from first principles if g of x is equal to minus 2x cubed. Same thing, x minus 3x squared. And then lastly, f of x is equal to 3 over x. So you guys can do these ones just for sort of like to see if the concept that I've just covered, I call these game challenges because we are doing, I mean, we have a belief most as these learners that we are here that maths is a game. It's to be played, guys, it's to be played. So once we know how to apply procedural concepts and follow through step by step, then we can do it on our own. And we practice so that we can make the maths permanent. Also so that we can play the game, and it can be more easier to play the game of first principles. First principles is a game, guys. There's a formula for it. It's in the formula sheet. All right, and there's no ways that you could write this incorrectly because the formula sheet provides the formula for you. You can actually look at it in the formula sheet and then write it out as you see it. You can sort out f of x on the side. You know what it is, it's given to you. F of x plus h, you can sort it out on the side using the very same f of x function. Just make sure that you don't make a mess up here when you are distributing with your signs and all of that stuff. Make sure everything is 100% okay. Then you simply go back and substitute in the place of f of x and f of x plus h and f of x. Remember this minus sign, however many terms follow f of x, you need to distribute that sign throughout, you see? And then, yeah, voila, your simplification should be good. It's distribution, like terms, highest common factor, cancellation, substitution of the zero when you can see that this has been simplified to its completion, and then the answer, no problem. Then with the fraction, if you remember what I said with the fraction, very important, we substitute f of x and f of x plus h. Then we use that addition and subtraction, cross multiply that, so that we get this. And remember what's in the denominator, we write the division sign, and then we write the fraction itself, and then we change the divide to multiply. Like terms result, there's a cancellation, and then ultimately that leads us to the beautiful answer there. After the cancellation, we're left with -2. That's simplified completely. Now we are ready. When we are ready to substitute the zero, this drops. You don't keep this around. This goes. The minute the zero is substituted in the place of h, then there's this thing, goodbye. Then we can write our answer. Okay, so please guys, do these ones on your own and give yourself a chance to write these down. You can screenshot and then you can do them in your own time, please. I want to move on to rules for differentiation. The rules for differentiation. Okay, are we okay? Can I move on to the rules for differentiation? Can I move on from first principles? you guys are the special guests, so you need to let me know in the comment section if it's okay for me to move on. If you're saying no, I will you guys, your wish is my command. I will hear from you. You let me know in the comment section. Okay, I don't know if the silence means that no or yes. No one's commenting anything. I feel so alone. No one is saying anything. Sure. Okay, you guys are like supermising me, like, yo, wow. Never seen such amazing in my life. My goodness. Samaria Kwaka. See, nothing. We can move. Don paper. I'm telling you, I probably would have just like decided to end the live right now, because you know, like when people don't say anything, I fear. Unless you guys are scrambling to write things, and it's more of like you guys are so focused, or it's that you are writing, and you know, and then I understand. But hey, no comment. I get scared. I get very scared. Okay. Differentiation rules. So life can be very easy, can be made very easy, okay? But the only thing with differentiation rules is that we have different notation that we need to be very much aware of, that we have for differentiation rules. So I'm going to look at different questions here. They all have to do with differentiation. So instead of using first principles, there's a much more quicker method of us being able to differentiate a given function, okay, or a given expression, or a given equation. So what we're going to do, we're going to look at those differentiation rules. So determine using the rules of differentiation. So now we have to differentiate the following using the rules of differentiation. So there is this notation which I want you to be very much aware of. So this one, we call it dy over dx. So in other words, what this is saying, it says differentiate y with respect to x. So in other words, differentiate y with respect to x. That's what this is saying, in other words. So if you look at, it says differentiate y with respect to x if y is equal to. So here's the thing. What are they saying? In this equation where y is the subject, so it's very important that if they are saying dy, that means y ought to be the subject for the given function. And then what do we have to differentiate? Which variable do we need to differentiate with respect to? We need to then differentiate with respect to x. So what you can see is that in the expression after the equal sign, this first term has x in it, the second term has x to it. So that means we can really truly differentiate with respect to x. So what's important is that in the given equation, we need to make sure that y is the subject. This here is basically saying we must make sure y is the subject of the equation. In grade 10, you learned how to make various variables the subject of the formula. Okay, so in this situation, all right, if we are going to differentiate y with respect to x, this equation must show me a equation where y is the subject, because the variable at the top that stands next to d means that particular variable must be the subject. The variable at the bottom next to d is telling me the variable that I need to differentiate with respect to. So that means it can't be, x cannot be the subject. X needs to be the component part of the expression, okay, which is very important. So now that we have this here, now that we have it, that y is the subject, the next thing we need to make sure that we need to do is we need to make sure that this particular expression does not have any variables of x in the denominator. No variable of x should be in the denominator. I cannot differentiate if the variable of x is in the denominator. No variable of x must be in the denominator. I can't have that. Okay? No, not at all. So to help with that, exponential laws and definition, they help a lot. Exponential laws and definitions. And the one definition that helps a lot is this one. A to the power negative 1. I'm sure you remember that a to the power negative 1. There was this definition that used to say if the base of a particular exponent is raised to a negative number, then the position of that particular base changes. So this a is currently in the numerator, but the answer, that base changes, moves to the denominator. Then the sign of that particular exponent, when that base changes its position, the sign will also change. So this a is an a to the power positive 1, but it's in the denominator, so we write this as 1 over a. Vice versa, this 1 over a can be changed to become a to the power negative 1. So this here is an important definition which you will use a lot in calculus when it comes to differentiating, especially if the variable of x is in the denominator. It can't be that we have the variable of x in the denominator. So to help us with that, so that the denominator does not have a variable, we basically use the exponential definition, this one. So let's go. Also, another thing, all roots as well need to also be converted and changed, very importantly. So look at this, guys. This is very important. Note what's going to happen. So I'm going to rewrite y is still the subject, okay? And the thing is, I cannot begin to differentiate, okay, with respect to x until I've made sure that this particular expression has a coefficient variable in for each term that is defined and distinct, and all roots are converted from root form to exponential form. So that's another thing. Root forms must be converted to exponential form. Root forms must be converted to exponential form. So there are two things here. We cannot differentiate until all variables of x, because we are deriving with respect to x, must be moved from the denominator, you know. And then secondly, all root forms must be converted to exponential form. Okay, so let's go. This root x can be written as x to the power half over what? Over 2. Hey guys, I hope you can see that. Okay, this square root of x can be written as x to the power half. And I want to remind you, if you've forgotten, from the laws of exponents, that if this was x to the power n and it was raised to, it was basically the mth root of x to the power n, then to remove that root, I write that as x to the power n over m. Do you still remember that? Very important concept there. This is from root form to exponential. Okay, so very important to know how to convert root form to exponential form. So yeah, this square root of x written as x to the power half, the 2 over 2 minus, look at this one, the relationship between 6 and x is multiply. Okay, what combines this 6 and this x to the power 3 is multiplication, right? So that means this x to the power 3 can be moved to the numerator. But when that happens, take note what happens to the exponent negative 3. I mean, to the exponent x to the power 3. Okay, so this is me applying the what? The exponential definition, which says if the base of a particular exponent, okay, is changed from one position to the other, what happens is that when that exponent changes from the denominator to the numerator, it could be vice versa, from the numerator to the denominator, it moves to the numerator, but then the exponent, the sign changes. Very important. Okay, so the exponent sign changes, right? So I'm very close now. Then what I can do, the x to the power half has a invisible one, which is 1 over 2. Okay, so what I'm going to do, I'm going to write 1 over 2 x to the power half. The coefficient of x is a half. The variable is x, the exponent is half, minus here, what's the coefficient of this x? It is 1. So I can write this wholly as 1 over 6 x to the power negative 3. Right, this is so important here, guys. Okay, because remember, we cannot write or derive until what? Until all variables in the denominator are moved, and secondly, all roots, all right, are also what? Changed to exponential form. And then the other thing is that there needs to be a clear coefficient followed by a variable for each term. If a term has a variable and a coefficient, then it must be clear what the coefficient is and what the variable is, minus the coefficient and the variable with its exponent. Very, very important. So this x to the power negative 3 is observed as an x to the power negative 3 in the numerator. This x to the power half is also observed as a numerator variable, okay, with this rational exponent. Very importantly, now we are ready guys, now we are ready to derive. You see this dy over dx. When I am ready to derive, then I write dy over dx. Now there is a rule called the power rule when it comes to differentiation. We call it the power rule. And I simply want to say the following about it. Okay, sorry. So sir, if the numerator was 2, was it going to be 2x minus 3? Okay, I'm not so sure. Don paper, what are you talking about? What are you talking about specifically? Okay, Don paper loses me there. I'm a bit lost about his question. It doesn't seem like he's around. It's like he left. Okay. Yeah, I'm not so sure what he was asking specifically. All right, so I was saying for differentiation there's a power rule. So when we are finally ready to derive, I just want to state how we go about this. When we derive, guys, okay, let's say this was f of x is equal to, when we are ready to derive, 1 over x to the power negative 3 over 6. So you are asking, so if the numerator was 2, was it going to be? Yes. It was going to be like that, Don. Yeah. So if the numerator here was 2 instead of this 1, then yes, the x would go up to the numerator. The x would go up to the numerator. And then when it goes up to the numerator, what would we do? We'd write this as 2x to the power negative 3. So yes. Yeah. So whatever that, whatever is, because, yeah. Okay, you got it. So this here, guys, what we do is we take this exponent, we write it as a coefficient multiplied by the present coefficient. So it's like this exponent comes down, it comes down and it gets multiplied to 2. The 3, the exponent comes down, gets multiplied to the current coefficient. Then the variable is retained, and then we subtract 1 from the exponent. So then what our final answer becomes, because of applying the power rule, okay, is that we get 6x to the power 2. That's how this 2x to the power 3 is derived, okay, using the power rule. So the power rule is exactly that. So if you have a to the power m, when you're deriving, you're simply saying, let's say there's n a to the, so this would be m times n a to the power m minus 1. Okay, m times n, so the m comes down, gets multiplied with the coefficient, and then you say m times n times a to the power m, a to the power m minus 1. Okay, so that's what we constantly do when we are deriving. So if you come here, what's going to happen when you start deriving? The half comes down, gets multiplied with the current coefficient, which is a half, and then we say x to the power half minus 1. Do you see that? Same thing here. We have a negative already for the minus 1 over 6, but the negative 3 comes down. So we have negative 3 into negative 1 over 6 x to the power negative 3 minus 1. This guy is this is the application of deriving using the power rule. Okay, so what did I say, guys? I said the exponent gets multiplied with the coefficient of the current term, which is a half. Then the x is retained, gets raised to the power half, but then we always subtract 1 from that particular exponent. Okay, so the only thing that really significantly changes is the fact that we take the exponent, we multiply with the current coefficient, retain the variable x, then we subtract 1 from the exponent itself. So hopefully grade 12s, this makes sense, the power rule, okay, when it comes to calculus. Very important. If you look at this negative 1 over 6x to the power negative 3, again, guys, what did I say? We take this negative 3, the exponent, we bring it down, it gets multiplied, so it's negative 3 times the negative half. Then we retain the x, raise it to the power negative 3, we always are subtracting 1. So let's finish off then, guys. What then is the simplified answer? 1 over 4x. You take your calculator. If you don't know what half minus 1 is, you should get a negative half. Okay, then here a negative times a negative gives me a positive. 3 times 1 over 6, your calculator should help you out a lot if you don't know these things, guys, off the top of your head. 3 goes into 6 2 times, so it's 1 over 2, but it's a positive 1 over 2, x to the power negative 4. Now, we don't end there. Okay, our final answer is, we prefer that final answers be written as a positive exponent. So we don't want no exponents being negative, but we want our exponents to be positive exponents. So when we finally write our answer, we have 1/4. Okay, this x to the power -half, which was in the what? In the numerator, can now be brought back to the denominator. And it joins what? Hopefully, obviously, it joins the coefficient in the denominator. So this x to the power -half joins the denominator. It becomes x to the power half plus 1/2x to the power 4. This also moves from the numerator, joins the denominator, and obviously the exponential sign will change. Okay, yeah, because this is applying this definition. Remember, this definition has to do with if your variable is raised to a particular exponent and you shift or move the position from the numerator to the denominator, that variable shifts to the denominator, but then its exponent will change what? It will change signs. Okay, so this is actually dy over dx. And even more mature learners, okay, usually are never content with actually writing that answer that way. They even take it to the level of actually making sure that, okay, it's 1/. Remember, that's x to the power half can be written as the root form, in root form, which is root x plus 1/2x to the power 4. So that would be what? Dy over dx. So guys, what's important here is that the minute you are ready to derive the expression, you must then write dy over dx. Okay, whilst you are busy still trying to make sure that the equation itself, where y is the subject, you are still working it to ensure that it is a expression on the left hand side which has what? Which does not have any variables in the denominator, which does not also have roots. Okay, but the roots are converted into exponential form. When you have fully simplified this particular expression, then you can go ahead and derive. And when you are ready to derive, you simply write down dy over dx, and then you proceed. So as a grade 12 learner, guys, as we do this, as we apply the rules of differentiation correctly, and also as we make sure that we utilize the simplification very easily, then you should have no problems, guys. Absolutely no problems. Okay, all right. So hopefully you noted the notation. Determine using the rules of differentiation dy over dx. So all dy over dx if y is equal to that. Remember, you are given an equation where y is the subject. Sometimes you may be given the equation and y is not the subject, but you have to actually make sure you manipulate the equation so that you make y the subject of the formula. Then you can only go ahead and simplify, and then only you can derive the particular equation with respect to x once this is ready to be derived. And then you apply the power rule for each individual term, very importantly, all right? And then you make sure that your answer is written so that at the end of the day, there are no negative exponents, and all rational exponents are then converted back into their root form. Very, very important. So that was a dy over dx scenario. But we are not limited to dy over dx. Look at this one. Use the rules of differentiation. Use the rules of differentiation to determine the following. Now I want you to take note of this type of notation that they have here. Okay, look at this one. This one has a capital letter D and then there's an X. Okay. Yeah, I usually post it up Molobi. I usually take these live sessions and I save them as downloads there on my YouTube channel. So I'll be compiling a playlist, okay, because I started with first principles and now I'm doing differentiation rules. So what I'll do is I'll compile a playlist on my YouTube channel for the grade 12s, just on calculus alone. It will be a grade 12 playlist for calculus, and this will be the first video that will be there. After I'm done with this live, I'll actually post it up there, and then I'll make sure to sort of distribute the news, you know, on my platform here on TikTok, just to let people know that that video is there for viewing at your own time. You can you can watch it at your own time, your own pace, and take it in. Okay, so this one, dx, okay, and then there's a bracket, x minus 2 into x plus 3, the close bracket. Now, I'm sure you see that the notation here is slightly different. The one that we just did said determine using the rules of differentiation dy over dx, and this was standing on its own. All right, now it's saying if y is equal to Modisemolobi, not today, but in a future life, maybe tomorrow, the same time, around about the same time in the evening, I'll check it out. If not tomorrow, then the day after, because obviously I'm trying to cover certain aspects of the calculus, and then I'll eventually get to differential calculus, the application type questions, no problem. So this one I was saying dy over dx if y is equal to, all right, you see the type dy over dx if y is equal to. So I had to actually take the y is equal to and simplify this equation for whilst y is there until I am ready to differentiate. When I am ready to differentiate, then what did I say? I said dy over dx equal, very important, then derived using the rule, you see, and then eventually got the answer. But even the final answer still had dy over dx. There is no y is equal to, there is only dy over dx as the subject until the end, because this is where differentiation started, and I basically have it until it ends, you see. Okay, now look at this one. The notation is slightly different. We have dx. So this simply means find the derivative with respect to x. Simply that. Derivative with respect to x. Okay. And what's beautiful here is that encased next to dx is the expression that I need to derive. And what you can see is that it only has x. So what I need to do is I need to simplify the expression. Okay, just like in the same vein, when I had y is equal to, I had to first simplify this thing. All right, so I'm going to simplify, and then hopefully when I'm ready to derive, then I'm going to show you what happens when I'm ready to derive. As you can see it, this is x minus 2 into x plus 3, which means I can still simplify this. So what you do is you keep dx until you are ready to simplify. You are ready to derive. So you must keep derive using power rule. So what you must do is you must keep dx, all right, and simplify this thing. You must keep dx until you are ready to derive using the power rule. So let's do this then. Let's keep dx and let's simplify what's in the brackets. X minus 2 into x plus 2 simply means we must use FOIL, because that's the simplification process we are going to take. We take with a binomial times another binomial, all right? So x times x is x squared. X times 3x, 3 is 3x. Minus 2 times x, negative 2x. Minus 2, negative 2 times positive 3, Negative times a positive is negative, and that's negative 6. Okay, so far so good. We still keep dx because we are not ready yet to derive with respect to x using the power rule. X squared plus x minus 6. Now I would say we are very much ready to do what? To derive with respect to what? To x. Now how many terms do we have inside the bracket? How many terms do we have inside the bracket? Okay, we have, I'm sure you guys, and I'm gonna wait until someone comments in the comment section. How many terms, guys, do we have inside this bracket? Anyone know? Thank you, Vudomi Nwakoni, for the follow. Really appreciate it. Maitseho, thank you so much. And Skulile, thank you so much, guys. I love this done paper. So yes, there are 3 terms inside the bracket. So now what we do is we derive with respect to x for 3 terms. We derive with respect to x for 3 terms. So in other words, you are going to derive each term using the power rule. Okay, so first things first, when you are now in the position to derive, dx falls away. So he falls away, and you just write equal. So this x squared, so I apply the power rule, 2, okay, remember there's a 1 here, 2 times 1 x to the power 2 minus 1. Okay, do you see that? This 2 comes down, gets multiplied, the coefficient that's invisible that's there is 1. Then x, then 2 minus 1 plus, there's an exponent 1 there, unseen. So this is 1, there's an exponent, there's a coefficient 1, x 1 minus 1. And then lastly, the derivative of a constant is 0, guys. The derivative of a constant is 0. So if we derive negative 6, we simply get 0. Okay, so we derive each term, the derivative of x squared, the derivative of x, the derivative of negative 6. Yes, indeed, always. It's always the case. All right, remember, for people it's a weekend, it's Friday, so yeah, people are making various musical noises, definitely. So 2 times 1, but don't be distracted, hey? Don't be distracted. So we have 2x there, 2 minus 1 is 1, plus we have x to the power 0 there, okay, and then this minus 0 is neutral, so we don't even consider it. Final answer, 2x. What's x to the power 0? It's 1, so that's basically 2x plus 1. That is what we get for the derivative. Okay, dx, the derivative, we get 2x plus 1. Okay, are we clear, guys? So this is very important, because with this notation, okay, dx, capital letter dx, has the expression that we ought to simplify and derive inside the bracket, and it's attached, dx is just attached to that. So what we do is we keep dx, we keep it, and we busy simplify, you know, this thing until we are ready. At this stage, we've gotten to a point where it's like we cannot simplify any further. There are 1, 2, 3 terms. Now all we need to do is we need to derive with respect to what? To x, using the power rule, and we derive each respective term. Okay, dx, please guys, when you are deriving, the dx must not be there. It must fall away. It must say goodbye, and then you know for sure that the person is deriving now. All right, so take note of the notation, because the notation, guys, whatever it is, we need to apply the right approach for whatever notation we are given. Okay, so hopefully you are feeling the mojo, because it's very important to feel the mojo. Maybe someone else is asking, say, what if I am given f of x is equal to x plus 1, the whole thing squared, and then they find the derivative using differentiation rules of f of x is equal to 7 x plus 1, the whole thing squared. Okay, so this is another sure, I'm glad on paper. This is obviously another situation where you are given f of x. So what you do is you also, because remember f of x stands for y, so that means you just need to simplify this first. So 7x plus 1, the whole thing squared, is 7x plus 1 into 7x plus 1. Then what do? You FOIL. Okay, get 49x squared plus 7x plus 7x plus 1. 49x squared plus 7x plus 7x plus 1. Simplified, 49x squared plus 14x plus 1. That is f of x. Now we are ready to derive. Now with this, we write f prime x when we are ready to derive. Then we do the deriving. 2 times 49 into x2 minus 1 plus 14x1 minus 1. I know masters that 1 times 41. I mean 1 times 14, which is 14. Plus what? Plus 0. Derivative of a constant is 0. Then you know most that you get 98x plus 14. All right, now obviously I know that would be x to the power 0, but I know x to the power 0 is 1. So you know, the more fluent you get with these things, then you you can kind of go ahead. That x to the power 0 we all know is 1, so therefore I write 98x plus 14. That was what? F prime x. So take note of the notation, guys. In this particular situation, because you are given the function f of x is equal to 7x plus 1, the whole thing squared, and then they say I find the derivative of the function. Okay, then of course all you simply do is you take f of x, you keep it with the simplification. You simplify until you get to the very last bit of simplification as far as you can. Then when you are ready to derive, you don't write dy over dx. You don't write, you don't force feed dx. All you simply do is you write f prime x when you are ready to derive for this particular situation. So you see, I'm looking at different scenarios here where we are given, these things, all right, as they are. So please, guys, make sure that you showcase, the application of the power rule, which is very important. You must show the application of the power rule, because that's what you are learning as a grade 12 learner, within the scope of the syllabus that you are doing. So it becomes very important for you to do that. Okay. Because it is Vutomi, it's very simple, like I think, remember, if maths is not simplified when taught, then how in the world do we expect even the weakest of learners to be able to understand it? So it's very important to simplify it. Maths is very simple. Maths is a game, Vutomi, hence the channel, hey? I'm just trying to really inculcate in the minds of everyone that maths is such a beautiful game to be played by everyone and anyone who wants to play it. Okay, let's say we are given this question. Y is equal to x squared let's say they did not say, they just say differentiate this with respect to x. Okay, they don't set it up for you like they did, for instance, for this question, where they say determine, use the rules of differentiation, dy over dx if y is equal to. With this one, there's no such. They're just saying differentiate y is equal to x squared minus 1 over 2x cubed. So maybe you're like sitting there and you're asking yourself the question, so how do I approach this particular question? So same thing, you would first keep the y is equal to, simplify, all right? And remember, what did we say? We said we do not want to see any denominators where there's a variable, okay, in the denominator. We don't want such. So the goal then is to take this x cubed, the 2 and the x cubed have a relationship of multiply. So this can be moved because it has that relationship. The inverse of multiply is divide, all right? So we can move and write the inverse. So x to the power 3 can be written as x to the power negative 3 in the numerator, if that makes any sense. Okay, so you can write 1 over 2. This becomes x to the power negative 3. Okay, and then now we are ready to derive. When we say y prime. Okay, this also means to derive. This is meaning the derivative. We are ready to differentiate with respect to that x. Okay, so this is another notation. Why? Because we are given this and we are told to differentiate, and we were not told dy over dx. We are just given y is equal to x squared minus 1 over 2x cubed. So we can simply just say y prime when we are ready to derive. And then what happens? Okay, now I'm sure you know what happens. Okay, for me, I know in my head it would be 2 times 1. So I'm just going to write 2x 2 minus 1. Okay. 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 Then when you get to a place where you know what you need to do, you can just simply write 2x, and you don't have to write 2 minus, because you know mentally what 2 minus 1 is. Okay, but obviously I show you what's done, because obviously we are still learning, right? So take a negative 3 comes down. Obviously that negative 3, whether it starts or it's at the beginning, doesn't really matter, because multiplication is commutative. The order of things when you place them, when you are multiplying, doesn't really matter. So the minus 3, some of you may be like, hey, but why didn't he put it first? Why is he putting it second? It doesn't matter, guys, right? Because at the end of the day, you just need to multiply the exponent with the coefficient. You retain the variable, you raise the exponent to negative 3 to that particular exponent, and you minus 1. So that would be x to the power negative 3 minus 1. Okay, then finally you get 2x minus, this here, the negative times the negative is a positive, so that gives us 3 over 2x to the power negative 4. Does that make sense? And then finally, the grand finale, 2x. Remember, we don't want any negative exponents in our final answer, so that's minus 3 over 2. The x goes back to the denominator. The exponent, that's negative. Remember, when the base changes position from numerator to denominator, the exponent loses that negative sign. It becomes positive. And that's it. That is basically the derivative with respect to x. Y prime is equal to 2x minus 3 over 2x to the power 4. Okay. Yeah, I do one-on-one, Vutomi. I do one-on-one. Just message me on the side. That's if you want one-on-one, or if there's someone that you know that wants one-on-one, you can do one-on-one. And then obviously there's a price attached to it, but yeah, we can talk on the side. You missed the step before the final answer, or because you were typing, trying to get the attention of the question. Okay, so the step before the final answer. So remember, with this here, at least I hope we were together here, that 2x raised to the power 2 minus 1. Okay, because remember we are deriving now, so the 2 gets multiplied So the 2 is the exponent, comes down to the coefficient, gets multiplied with the coefficient, which is there, which is 1. 2 times 1 is 2. Retain the x, raise the 2 minus 1. So we subtract 1 from the 2 all the time. Minus -3 comes down, gets multiplied with -1/2. X to the power, that -3 we minus 1. Then obviously, ultimately, that gives us 2x. 2 minus 1 is 1. Minus negative times a negative. Ooh, do you see what happened there? We made a big mistake and nobody even told me in the comment section, no sir, the sign is supposed to be positive. Okay, negative times a negative is positive, guys. Very, very important there. Very, very important. Negative times a negative is positive. So we get 3 over 2 there. X to the power, what's minus 3 minus 1? -4. Then I was saying that our final answer will never be written with a negative exponent. So this x currently is a variable that is in the numerator. Okay, that's where its current position is. So when we write our final answer, we make sure that that exponent needs to change from negative to what? To positive. We write our answers as positive exponents, very importantly. So this x moves from the numerator, goes down to the denominator, but when that happens, according to the definition of exponent, the variable, when it moves or changes position either to the numerator or the denominator, the exponential sign always changes from what it is to something else. So since it's -4, the exponential sign after the variable has moved to the denominator becomes a +4 exponent in the denominator. And that's it. Okay, so the answer is 2x plus, remember, because that negative times the negative gives us positive, plus 3 over 2, the variable x in the denominator. The exponent -4 is now positive in the denominator because initially the variable was in the numerator. Okay. So I hope that makes sense and is sensing. If you are talking about matrices, currently, yeah, I'm just helping out grade 12 learners, high school level, and it's what you might call. Man, was that a gunshot? Sure. Okay. That's crazy. Okay, so yeah, that was that. It is indeed. It's a game for sure, guys. It's a game that should be beloved and played by all. All right. Yeah. So let me do this, guys. Let me leave you with a game challenge for these types of problems, and then let's call it a night. I'll pick up on this tomorrow again. Actually today, later on though, in the evening, around about the same time, so after 10. Yeah, this was calculus, but it was just the beginning parts of calculus. We did first principles and we did differentiation rules. So that was just that today. Then we'll pick it up from where we left off with other stuff. So let's do some game challenge. Let me give you some day game challenges. Differentiate the following using the wholes. Okay. So hopefully you guys have noted some of the things that I said here. Notation is very important. All right. Very important. So I gave you game challenges on the first principles. Hopefully you guys took snapshots of those. Okay, I think that's it, guys. I'll leave you with that beautiful, okay, maybe 6 is a good number. Let's do these, guys. That's I guess those are the problems you get. I mean, those are the game challenge problems. I'll leave with you for differentiation. Remember, guys, this is just bare minimum. This is just to sort of like facilitate. This is just to facilitate work in the direction of what we covered. So. Remember that this does not mean that so these are the questions that I may potentially. No, obviously this is just bare minimum. This is just to hammer in the concept that we've just covered, so that I can be sure that we see what it is that we ought to do. But then it is your prerogative that you make sure that you do the things that you ought to do. Okay. Yes, it is free marks. Differential calculus is a lot of free marks, and I'm happy that you guys know that. So I'll see you guys tomorrow then. Yeah, so I think I started up this live session around about 10:30 to 11. So let's say 11 o'clock tomorrow, midnight, towards midnight time. I think it's a good time for me personally to help grade 12 specifically, so we can make that a consistent standard time. Take it from 11 until 1-ish, we'll see. Okay, so tomorrow, guys, I'll see you again. We'll do the corrections to these game challenges with your help, of course. I don't think I'll do them myself, with your help, so that we can see that people grasp the concept. So let me see you guys tomorrow, hey? But take care. It was great. Thank you again for giving me the time, being an audience. Have a great one. Cheers. Thank you, Totonic, for the follow. Thank you for all the follows, guys. Yo, Lusanda, thank you so much for the follow. Rest Prosper for the follow. Yeah, we got a few followers today. Makulu say, yo, Samazi, wow. Vutomi, right, awesome. Yo, thank you, guys. Cool. Tami, got some digital marketers coming in here. Usimuzi, thank you. Vutomi, thank you. Salim, MK, thank you. Yeah, we had a few people follow today. Ntombi Kanyile. Yeah, we had a few followers today. My goodness. No, thanks a ton. Don Paper. Yeah, you're welcome, bro. Welcome, Don. Yeah, I'm sorry for those people that came in here. People that came in here that kill me. People ask a lot of mathematical questions related to like other level mathematics. That's not high school mathematics. I'm glad that people can actually ask those types of questions, but yeah, people just need to understand that I'm operating within the scope of the high school phase. Because my passion and my love is to help kids in the high school phase. Yeah, especially grade 9s, 10s, 11s, and 12s. Not so much grade 8. Yes, grade 8. I just feel like grade 8s need to get they just need to be brought in the high school phase first. They need to get familiar with the way that they are taught, and then their teachers at their respective schools. Then I'll come in and start helping out with the grade, with them, that much more later on in life. So Gladys, I just did grade 12 now, actually, calculus. So I'll post up the video in the YouTube channel. I'll save and then post up the video just now. But I was doing calculus just now, so I'll continue tomorrow with grade 12 again at 11. I'm sorry, Gladys, that you missed it. Okay, I can see your hand though, your profile picture hand. That one that's like the Dutch Londe, if you know what I mean. But yeah, you'll be okay. You missed it, but you can always check it out in the channel, the YouTube channel. I'll start a playlist for the grade 12s with the calculus videos. So this will be the first, and then the others will follow as time goes by. But these are the game challenges I left them. Left them these game challenge problems that you see on your screen. That is for the rules. Okay, and applying the differentiation rules, and then I had given them a game challenge earlier on for first principles. That was first principles game challenge, that number 1, and these ones. Okay, all of these ones. Okay, all of these ones. It wouldn't make sense to say find f prime x if f of x, but then I wrote g of x. Can't make sense. So this was first principles. I wanted you to use first principles with these ones. Then I'll pick up from there where we left off, and we'll do other stuff as well. Okay? But that was just the intro. Thank you. Stay awesome, guys. Thank you again. Yeah, and then get other conversations related to other things. Oh, you did? That's great. Thank you. You are quick with your hands, Miss Gladys. I love it. Cheers. Okay, guys, let me check you out. Bye.